Hello everyone, my name is Osama Samara, and today we're gonna look at a problem that deals with fatigue failure analysis from the course ME3190. So for this problem, we have a shaft A and it's welded to a fixed support right here, and it's being loaded by force F. We have a stress concentration factor, KTS, of 1.6, and it's induced in the shaft by the fillet of radius 1/8, and the length of the shaft, this one, shaft B, is 2 inches in total, and the load F cycles from 150 to 500 pound force. And the problem is asking us to find the factor of safety using the modified Goodman fatigue criterion and using the Gerber fatigue failure criterion. Right, so we noticed from this problem it says the load F cycles from 150 to 500, so this is not a reversible load. This is actually a fluctuating simple loading, right? And we know the formula for that one. We need to calculate the mean stress, which is equal to sigma max, right? Let me try to sigma max plus sigma min over 2, and we need to calculate the alternating stress, which is equal to sigma max minus sigma min over 2, right? But for looking at our problem, we notice that we only have a shear stress, right? We don't have any bending stress or normal stress, so we can simply rewrite these equations using tau, right? Tau, or the mean shear stress, is equal to tau max plus tau min over 2, and for the alternating shear stress, same thing, tau max minus tau min over 2. Right, so we need these two equations so we can find the factor of safety. Okay, moving on. So for our problem, we're trying to calculate tau max, right, and tau min. And we can simply find these two using this equation for torsion, right? Since the bar is twisting, right, we have torsion. So for tau max, it's gonna be T max R over J, right? And T min R over J, with R being the radius of the shaft, shaft A, and J is the polar moment of inertia, right? But for this problem, we have a fillet and we're given a stress concentration factor, right? So we have to account for that in our calculation for the shear stress, so we have to add KFS to both equations, right? So let's analyze these two equations. R is given, the radius of the shaft, polar moment of inertia is a constant, we can find that. T max, or the maximum torque, we can also find that, right? The only thing, or the minimum torque, we can find that. The only thing we're missing is finding the shear stress or the concentration factor, right? Or the fatigue stress concentration factor, which is KFS, right here. So let's calculate the maximum torque. Tmax is equal to the maximum force times the length, right? Force times distance. And our distance is 1 plus 1, so 2 inches. Right, so we have the maximum force is 500 times 2 inches. That's going to be 1,000 pound force inch. Right, and the reason we used 2 is, remember, these two forces are in the opposite direction. So it's like they're helping each other out. So we can use force times this distance, so 500 times 1 plus 500 times 1. So 500 plus 500 is 1,000, same thing. Right, and let's do minimum torque, which is minimum force times length, and that's going to be equal to 150 times 2, and that's 300 pound force inch. Right, so we're good there, and let's find J, right? Let's find all the constants in our formula, and J is just pi r the fourth over 2, and if you substitute J right here and you simplify it, the formula becomes tau max is equal to 16, right, KFS Tmax over pi d cubed, with d, try to fix that, pi d cubed, with d being the diameter of this shaft, right, A, which is 7/8 right here. Right, so we're good on that one. Diameter is given, 16 over pi are just constants. Let's find KFS. And if you guys remember, let's move on, next slide. Let's find the fatigue stress concentration factor, right? KFS is equal to 1 plus Q times KTS minus 1. If you don't remember this formula, you can just check the roadmap in chapter 6, right? If you open textbook, the Shigley's book, and you go to the roadmap in chapter 6, the very last section in chapter 6, it summarizes all the chapter for you, and it gives you all the important equations, right? And this is one of them. So with the Q being notch sensitivity, and KTS is given in the problem of it's 1.6, I believe. Yes. Okay. So how do we find the notch sensitivity? Well, you also have an equation or a formula to find the notch sensitivity, and it can be found in the roadmap in chapter 6, right? and it's governed by this formula right here, with r being the radius of the fillet. Right, and same thing, how do we find square root of a? It's also governed by a long equation, which can be found in the roadmap. So make sure you guys check the roadmap, really important. I'll just write it down. The equation SUT plus 1.35 negative 5 SUT squared, with SUT being the ultimate tensile strength. So 2.7 10 to the negative 8 SUT cubed. Right, we know the ultimate tensile strength. In our problem it was given 55 KSI. Right, so if you plug this into your calculator, you'll end up with 0.088345, right? So you can plug this one back here, and for R, it's equal to 1/8, right? The radius of the fillet. So if we go back to our problem, radius of the fillet is 1/8. Okay, if you do the calculations, you'll end up with a notch sensitivity of 0.8. Right, so let's try to calculate KFS. Q being 0.8, KTS, it's 1.6 minus 1, and you'll end up with a 1.48, right, for KFS. So let me try to rewrite that, 1.48. Here it is, 1.48. Right, so looking back into our equations, the only thing we were missing is KFS. Now that we have KFS, we can calculate tau max, right? Same thing for tau min. 16 times KFS T min over pi T cubed, right? So let's try to find tau max and tau min. Remember, it's 16 times KFS, which is 1.48, times T max, or the maximum torque, which is 1000, over pi D cubed, and D is the diameter of the shaft, which is 7/8 cubed. Right, same thing here, 16 times KFS, 1.48, times 300, I believe, the minimum torque, yes, 300 over pi times 7/8 cubed. And if you do the calculations, tau max will end up to be around 11.25 KSI, right? And this one, tau min, it's going to be 3.38, around 3.38 KSI. Right? So here's tau max, tau min. Let's go back to our formula. Since we have this tau min, we can calculate the mean shear stress and the alternating shear stress. Let's try to do that. The mean shear stress is equal to tau max plus tau min, so 11.25 plus 3 0.38 over 2, and that's equal to 7.32 KSI. That's your mean shear stress. Let's calculate alternating shear stress, which is governed by the equation or the formula tau max 11.25 minus tau min, which is 3.38 over 2. You'll end up with an alternating stress of 3.4 KSI. Great. Now that we've found tau min, or the mean shear stress, and the alternating shear stress, we can go ahead and use the fatigue failure criterion modified Goodman and Gerber, right? And let me pull up the equations for modified Goodman. Right, so for modified Goodman, we're not using normal stresses here, so alternating stress over the endurance limit, SC, plus tau m, the mean shear stress over the ultimate, right, tensile strength. But since we're using shear stress, right, instead of normal stress, we need to use SSU, not SUT, right? SUT is the ultimate tensile strength. SSU is the ultimate shear strength. And why do we use SSU instead of SUT? Because we're dealing with shear stress, right? And this is going to be equal to 1 over n, with n being the factor of safety. And this is modified Goodman, right? So, and for the second part of the problem, we're going to use the Gerber fatigue failure criterion, which is governed by this equation, n tau a over SE, the endurance limit, plus n tau m over SSU squared equal to 1, and this is Gerber. Right, so looking at modified Goodman first, let's do part A. We know the alternating shear stress, we know the mean shear stress, and SSU can be found using this relation. SSU is equal to 0.67 SUT, right? And yeah, you can find this in the roadmap in chapter 6, right? Last section, chapter 6. And you can plug in SUT, 55 KSI, and if you punch in the numbers into your calculator, you'll end up with 36.9 KSI. Right. So we know this. We know this one. We know the alternating shear stress. Now we have to calculate the endurance limit. Right, and let's try to find the endurance limit. So let's do endurance limit. Once we find the endurance limit, we can calculate the factor of safety. Right, so if you guys remember, first step is SE prime, which is the endurance limit of the test specimen, is equal to 0.5 SUT. And if you plug in 55 KSI here, you'll end up with 27.5 KSI, and that's the endurance limit of the test specimen. Now let's find the endurance limit for our actual piece, and it's governed by this formula. SC is equal to KA, KB, KC, KD, KE, KF, SC prime. Well, we know SC prime, it's 27.5. Let's calculate the modification factors, right? Ka, Kb, and Kc. So for Ka, it's called the surface factor, right? And Ka is governed by this equation, A SUT B, and this depends on the surface finish, right? This is surface factor, Ka, and it's governed. It's it's related to the surface finish of our material. So let's go back to our problem. The material is hot rolled, right? So if you check our textbook, it's going to give you the values for A and B for a hot rolled surface finish, and A is going to be equal to 14.4 and B is equal to negative 0.71. So A is 14.4, and this can be found from our textbook, 27.5 SUT, or no, it is actually 55, right? SUT is equal to 55 and B is equal to negative 0.71. You do the calculation, it comes out to be 0.81. Here's your Ka. Let's find Kb, and Kb is called the size factor, right? And it's governed by this equation, right? 0.879 dE. Let me try to fix that. The effective diameter, dE, power of negative 0.107. Right, and why do we use the effective diameter here to find Kb instead of using the diameter for the shaft A? Is because, remember, this shaft is not rotating, right? It's fixed right here. This is fixed. That's why we need to find the effective diameter. If you look into our textbook, if the shaft is rotating, you can use the diameter of the shaft, right? But since this one is not rotating, you need to find the effective diameter. Right, so let's continue here. How do we find the effective diameter? Also from a table in our textbook, right? From chapter 6, if you go to 6-9, section 6-9 in our textbook, look, has a table that tells you how to calculate the effective diameter. So looking at the table, the effective diameter for a cylinder is 0.3, or for a circular cross section it's 0.37 times the diameter of the shaft, which is 7/8, and that's going to be equal to 0.324. So it's equal to 0.324 inches. Right, so KB, if you plug that back into our equation, KB will come out to be 0.99, so very close to 1. Okay, and KC is called the loading factor. So it depends on the load, and in our case, if I look at the textbook, right, for KC, torsion, for bending it's 1, for axial it's 0.85, and for torsion it's 0.59. And we're dealing with torsion in our problem, so it's 0.59. Right? So KC, we know that one. KD, we can cross that one. No information is given about the temperature, right? And no information is given about reliability, KE, and no information is given about corrosion or other miscellaneous factors. Right, so we'll end up with, let's do it right here, SE is equal to KA, which is 0.81, times KB, which is 0.99, KC is 0.59, SC prime is 27.5, right? And SE will end up to be 13, yes, 13 KSI. Okay. And now we're good, right? We can use the modified Goodman failure criteria, right? N is equal to 1 over tau A S E, right? SE. Trying to rearrange the formula to solve for the factor of safety. So tau A over SE, the mean shear stress, tau M over SSU, the ultimate shear strength. Right? So let's find that one, and this is part A using modified Goodman, and that's equal to 1 over 3.94, right, for tau A. Let me double check, right, tau A right here, 3.94, tau M is 7.32, and SE is 13. So 13 plus 7.32 over SSU, which came out to be 36.9. Double check, yes. SSU is equal to 0.67 times SUT, the ultimate tensile strength, came out to be 36.9. And this will give you 1.99, right? This is using modified Goodman failure criterion. So for part B, it's asking us to find the factor of safety using a different failure criterion, which is Gerber. So I'm trying to rearrange the formula using the Gerber failure criterion, and it's gonna be rather a long one, right? So if you go back, go back here, right? This is the Gerber failure criterion, and we're trying to solve for N, right? So a lot of algebra is involved here. So for part B, Gerber, it's gonna be n is equal to 1/2 SSU over tau m, or the mean shear stress, squared, tau a, the alternating shear stress, SE, times -1 square root 1 plus 2 tau m SE over SU, or rather SSU, right, tau a squared. Right, and if you plug in all the values for tau m, SSU, tau a, SE, same thing here, and you punch all the numbers into your calculator, you'll end up with a factor of safety 2.49. Right? So your part will not fail due to fatigue. It's about larger than 1. Same thing for modified Goodman, it's larger than 1. So I hope you find this video to be helpful. A couple of takeaways from this video is make sure you look into your textbook, right? Chapter 6 to find all the equations used here, and make sure you take a look at the roadmap, right, in chapter 6, and that's the last section. Chapter 6 lists all the formulas you need, and it's a pretty good summary, so I recommend you take a look at it. Right, thank you. Have a good one.